Now let's apply that analysis we had from the last slide to a real circuit. We have a sinusoidal voltage source with amplitude of 10 and phase shift of 30 degrees with an internal resistance of 25 ohms, and we connect that to a 100 ohm load via a transmission line that has a characteristic impedance of 50 ohms and is lambda over 4 wavelengths in length. What we want to determine is we want to find the general equation for the voltage along the transmission line, and we also want to solve for the time domain expression for the voltage at the load. So this is a lossless T-line because we see that Z0 is real, so we're going to use the lossless simplification, and what we'll then write is V of Z is equal to V bar plus times e to the minus, and here's the simplification. We don't have to put gamma in there, we put minus j beta z, and then we have the reflection coefficient at the load, e to the plus j beta z. So that's our lossless approximation since Z0 is real. What we want to first do is find the reflection coefficient. So the reflection coefficient at the load is given by ZL minus Z0 over ZL plus Z0. It's 100 minus 50 over 100 plus 50. So that's 50 over 150. So we've got a reflection coefficient of 1/3. It's purely real, which means 1/3 of the incident voltage wave gets reflected back, and no phase shift occurs during that reflection. The next thing we'd like to calculate in this is what is V bar plus. So V bar plus, the equation that we developed from that is that voltage divider between the input voltage and the input impedance, right? So it's equal to V in over E plus gamma L, but gamma L is just J beta L in this case, since it's lossless. So we have a length and a beta. What we need to determine here is V in. So V in comes from that voltage divider, like I was saying before. That's the VSS times whatever the input impedance of this circuit is, divided by this plus Z in. So now we need to determine Z in. So from Z in, we're just going to use our general formula for a lossless transmission line. So that was Z0 times ZL plus JZ0 tangent of beta L over Z0 plus JZL tan beta L. So we just plug and chug here. Zn is equal to 50 times 100 plus J50 tan. Let's look at beta L real fast. Remember that beta is equal to 2 pi over lambda. Therefore, beta times L, where L is equal to lambda over 4, is 2 pi over lambda times lambda over 4 is, the lambdas cancel, or 2 pi over 4 is just pi over 2. So we plug in a pi over 2 here. Now we get 50 plus J100 tan of pi over 2. And plug that into your calculators and you get the fact that the input impedance is 25 ohms, or the result that the input impedance is 25 ohms. So we can now calculate the input voltage. Vn is equal to, it's going to be 10 e to the j 30, right? That's the phasor formation of that, t 10 e to the j 30. So we take that, the source voltage, we multiply it by 25 and divide the result by 25 plus 25. And so that's just going to scale this by 1/2. So we get 5e to the j30 is the input voltage. And therefore we can calculate, now we can go back and calculate V bar plus the magnitude and angle of the incident voltage waves. So V bar plus is going to be equal to 5e to the j30 over e to the plus j. Remember, in this one, beta L is that full length, and we calculated that result is pi over 2. So that's e to the j pi over 2, plus reflection coefficient at the load, which is 1/3 at an angle of 0, so just 1/3, e to the minus j pi over 2. So we'll just plug it in there. And if we do that math, we find that V bar plus is 7.5 e to the minus j 60 degrees. So our full equation for voltage, we can just write into this now, right here. It's V bar of Z is equal to 7.5 e to the minus j 60, so that's that incident voltage phasor, times e to the minus j beta Z plus 1/3 e to the j beta Z. And we could separate these out if we wanted to, and this would be equal to 7.5 e to the minus j 60 e to the minus j beta Z plus 2.5 e to the minus j 60 e to the j beta Z. And if we were to transform that back into the time domain equation, we would find that V of Z comma t is equal to 7.5 times the cosine of omega t minus beta Z with 60 degrees of phase shift plus 2.5 cosine of omega t plus beta Z also with 60 degrees of phase shift. This is in volts. So if we had information about propagation velocity and frequency, we could have calculated what omega t and beta were and written the complete formulation for voltage, but we weren't given that information in this equation or in this problem statement. We were, however, asked to determine what the voltage at the load was, and so that's just V of L equals 0, comma t. So voltage at the load is when Z equals 0. So that's just going to be equal to 7.5 cosine of omega t minus 60 degrees plus 2.5 cosine of omega t minus 60 degrees, and that's just going to give us 10 cosine of omega t minus 60 degrees. So that's the voltage at the load. So that's the full calculation there. So we see what happens in this case is that in the lossless transmission line, what happened was that the voltage that appeared at the load was just phase shifted from this by 90 degrees. That was the end result of that application.